Good stuff.
No, I'm not speaking. No,
Right, it's like
right. Because you can do it without, no? But then you're dealing with morphisms. So like, when we do this protoidal thing to separate morphisms that we want to be really like.
You're sure it's not about what I think it's about?
I'm pretty sure, yes.
All right. Well, then I have to
Check, double check.
this is like sequencing in parallel, and then out.
That's tomorrow. That's
Right,
tomorrow.
right,
Let's
right.
wait for them to come back.
Right. Because the thing is, I'm going to put some
Okay,
things
cool.
in.
All right, yeah, let's go talk about it.
There a room to talk about stuff?
Can we drink these later? Hey,
And then the thing I want is
we're gonna get
I
around.
have no internet, so I feel like they shot
I have no internet. So
an arm
no
of
edge
me or something.
pass in the middle a whole. I'm going to put just the input on the output.
Yeah.
So for any duoidal expression, I have a appreciate. Not only that I have duoidal expressions. Also, I have for any.
Such a lovely talk, thank you so much.
Structure for instead of monoidal, like as an alternative to monoidal structures. That here to me, where like why it's kind of like giving you functions and functional programming, and then you can use them however you want.
Right.
And I'm just wondering if there's any kind of point of
There is
connection
a relation to that. Who doesn't appreciate that approach? So there is that in string diagrams, but this is not very satisfactory.
No, I hear
So
you.
it simplifies a lot the story to not work with. Even if you have it there. So it's that intuition has a theorem behind.
Okay.
Like we know that protoids have. I'm going to start
Yes, I
calling
should let you
people.
track down your.
Thank you. Thank you for the question.
Thank you for taking the
That's
time.
what I did. Nicole, can you hear me now? Can you hear me? Can you hear me, Cole?
Yes, we can hear you.
Okay, perfect. So let me wait a second. So if people is arriving.
I guess they don't see you don't see our meeting chat, do you? On our shared screen? Just the slides.
Yeah, I can see you can see their thing, our screen.
Okay. Yeah, they don't see it. Just wondering if
Then I'm going to start.
show up.
Okay, so welcome to this first regular session. We're going to have 3 talks. Each one of them is 30 minutes. So we will have 25 minutes for the talk and 5 minutes for questions. If you have more questions, you can also ask them on the Zulip room. So our first talk is called Comfort with the Algebra of Stabilizer Codes. So take it off, Cole.
Thanks for the introduction, Mario. Yes, I'm gonna give this talk in 3 parts. The first is going to be a review of graphical linear and graphical affine algebra. The second is going to be a review of this work by Alex and I on graphical Lagrangian algebra. And then the third part is going to be the new work. And also I'm going to try to relate this talk to Priya's talk in the previous session. So I'm going to kind of have running examples with concurrently with quantum and electrical circuits. Yeah, so the way that I'm going to think of like all linear stuff in this talk is using pictures. So there's this way to regard the category of matrices as a prop. So given a field K, the matrices over that field K are generated by these like copying comonoids, addition monoids, which are both commutative. And then for every scalar in the field, the convolution of these two things is the addition, and 0 is like the co-unit and unit, and then they form algebra such that you have like the equations of the ring on these scalars, and then all of the scalars are natural with respect to these generators. So like, I don't expect you to remember all of this, but just to kind of give you a feel for how you can do linear algebra using pictures. So for example, if you have these generators, the way to think of them is you can kind of label the bottom wire with an element of your field. And then if you meet this white comonoid, then you kind of copy it through. And with this white counit, you kind of just forget about it. And then with the black monoid, you add the 2 elements, and the unit for the black monoid, you just kind of insert 0. And then when you reach this scalar, then you multiply by the scalar. So if you have like this string diagram on the left, then you interpret it according to these rules. So you plug in an A on the bottom, you copy it, multiply it by B. So that's the first component. And the second component, take the 0, multiply 0 by C, which is still 0, and then add A to get A plus 0 is equal to A. So it's this matrix here, because it's A times B plus 1. Okay. So I'm going to care about more than just matrices. I want to present linear subspaces using pictures. So there's this prop of linear relations where the morphisms are linear subspaces. So if you have a map from n to m, then you should think of it as a linear subspace of k to the n plus k to the m. And then the way you compose these subspaces is by tracing out along. So if you have one from k to the n plus k to the m and one from k to the m plus k to the l, then you compose by tracing out along the elements of k to the m. So this is like the relational composition of sets. And this gives you back linear subspace. And in fact, there's a presentation for this prop, and it's given by, you take the generators and relations of I should say matrices, and then you take the generators and relations of matrices off. So like these guys, and then you flip them around vertically, and then you impose these extra equations that make the white monoid and comonoid into an extra special Frobenius algebra. So you can kind of fuse them together using the spider law, which Priya talked about. And similarly for the addition monoid and comonoid, you fuse them together, and then scalars disappear. And then if you have like a scalar and you flip it over, that's the inverse if it's invertible. So just to give you a feeling for how you can do kind of this calculus of linear subspaces, all just using pictures. And here's an example here. So the way to interpret this is you draw like labels for the elements of your vector space on the bottom and on the top. And then when you meet the white spider, then you impose the equation that all of the wires are equal to each other. So this says A1 is equal to A2 is equal to B1. And then when you meet along the gray spider, then you impose that the sum of the elements on the bottom are equal to the sum of the elements on the top. So then you get that this diagram is interpreted as a linear subspace hollowed out by these equations. And so a bit more recently, there's been work on affine graphical affine algebra. So instead of the morphisms being linear subspaces, now they're affine subspaces. So what does that mean? You take the same presentation for linear relations, but now you add like a label onto the addition spider. And the way that we interpret that label is, so it's an element of the field. And then if we interpret it as a linear subspace, then we ask that all of the wires on the bottom and on the top sum to the same thing, except in addition, now there's this sum with, you add C to the one side. So that's like the affine shift. And there's more equations that this satisfies, which are, if you have two spiders with these phases, if they are connected together, then the phases sum together. And also if you have like this affine shift by 1 and you multiply it by C, that's the same as an affine shift by C on the spider. So these top ones are kind of like more like syntactic sugar. And then these bottom identities are, the first one is if you multiply by 0, then everything kind of disconnects and deteriorates. And the other two are saying that you can copy and discard the affine shift. So here's another example. So I've taken the same example as before, but this time I've like added this C, which is the element of the field, to this gray spider. So if you try to calculate what the affine subspace is corresponding to this diagram, then you like label all of the ingoing and outgoing wires by the ingoing by A1, A2, A3, and outgoing by B1, B2, and B3. And then when it meets this white spider, then you impose the equation that they're equal, the ones that are connected to it. And then when it meets this gray spider with C, then you take the sum of all the ones on the bottom plus C, and you impose that that's equal to B2 plus B3. So this is kind of the base structure, which I'm going to be working with throughout this talk, just for matters of calculation, and even just describing certain linear subspaces. Okay, so that was like the background on graphical linear and graphical affine algebra. And I'm going to make a quick excursion into linear symplectic geometry. And then I'm going to try to build this back up using this graphical algebra. So a symplectic vector space, at least in finite dimensions, you can consider it as a vector space with even dimension. So the dimension is 2, it's k to the 2n. And then there's this linear map called the symplectic form, which evaluates elements of the symplectic vector space as follows. And the way to think of this, or one way to think of this, is in terms of the phase space of a mechanical system. So because the dimension is even, and you can kind of grade the vector space into two parts, one being position and one being momentum. And then the elements of the vector space are like all of the possible configurations of position and momentum of your mechanical system. And this weird symplectic form arises by, you can think of it as the volume between elements in the phase space. So if you have some point Q and P in the phase space, so with momentum Q and position P, at another point with momentum Q prime and position P prime, then like the symplectic form between these two elements of the phase space is in some sense the volume. So I've drawn this this shape, which is the volume between these 2 points P and Q. So I'll try to like go along with this intuition for what the symplectic form means. And I've taken this table from Bayes and Fong's paper, I think passive compositional semantics for passive linear networks or something like that. And these are all different like translations between different types of mechanical systems and what the position and momentum look like in these settings. So one example I'll come back to is electronics, which came up in Priya's talk earlier. And P is apparently the flux linkage and Q is the charge. But if you look at the like differential with respect to time, then the position is the voltage and the momentum is the current. And in like translational mechanics, it's force and velocity, or position momentum, angular velocity, flow, pressure. So there's all of these kinds of different semantics in which you can interpret this symplectic geometry, at least. And I'm just going to consider for now the linear symplectic geometry. So just for the phase space, it's a vector space. And there's notions of like of morphisms between symplectic vector spaces. So in particular, a symplectomorphism is a certain type of linear map between symplectic vector spaces that preserves the symplectic form. So one way to think of this is that that's the preserved volume. And this has some physical interpretation in terms of what is like the deterministic evolution of the phase space. Because if you don't preserve volume, then kind of classical mechanics just breaks in a sense. So this is needed. And more than just linear maps, you can also talk about linear subspaces between of a symplectic vector space. So there's this notion of the symplectic dual space. If you have a linear subspace of a symplectic vector space, this symplectic dual space consists of all of the points in the phase space that are orthogonal to that subspace with respect to the symplectic form. So you can kind of think of this as like it's like the orthogonal dual of a linear subspace, except instead of being with respect to the normal like inner product of matrices, it's with respect to like this symplectic form that I brought up here. And this induces three important types of linear subspaces of symplectic vector spaces. Firstly, an isotropic subspace is one that's contained within its dual. A Lagrangian subspace is one that's equal to its dual. And then a coisotropic subspace is one which contains its dual. So in particular, subspace that's isotropic and coisotropic is Lagrangian. And the way that I want you to think of these is kind of as generalizing symplectomorphisms. So whereas a symplectomorphism is a linear map between vector spaces, all of these three types of subspaces are like somehow constraints on the phase space. So it's not like a deterministic thing, but it's almost like a non-deterministic kind of linear constraints with different levels of relaxedness. So in particular, coisotropic is like the most relaxed. Lagrangian is like a bit more strict, and then isotropic is kind of like co-relaxed in a sense. So I'll come back to this in a bit. And so because we talked about linear relations as being a category, so there's this prop given a field K where the maps are linear subspaces. So we can kind of augment this a bit and ask, now the maps are not just merely linear subspaces, but they're these Lagrangian subspaces. And this forms a category like with the same composition being the relational composition. And in this paper by Alex and I, we characterized in terms of pictures what these Lagrangian relations look like. And they occur by having a linear relation G and then doubling it with respect to this orthogonal complement functor, which you can see as like the thing that swaps the colors. And then you kind of trace it out with respect to this A on the one side, where A is like a bunch of invertible scalars in the field. So in some sense, you can think of Lagrangian relations as being a certain doubling of linear relations. Now, if you imagine that there was this no cap in the middle, then that would be like the embedding of linear relations into Lagrangian relations by this doubling. So there's kind of a copy of linear relations inside of Lagrangian relations, but this trace adds more stuff. And if we had affine behavior, so that the maps are not just linear subspaces, but they're affine subspaces whose linear part is a Lagrangian relation, then also we characterize what these look like. And you can think of it as being generated by these two Frobenius algebras, which are labeled by two elements of the field, and they're interpreted as the following affine relations. Yes, so it's like, remember how we got from linear relations, you have these two Frobenius algebras, and then affine relations, you add a phase to the spider, and then affine Lagrangian relations, now you add two phases to both of the spiders in some sense. And going back to Priya's talk, if you take certain nice idealizations of wires, resistors, capacitors, inductors, capacitors, voltage sources, and current sources, then you can interpret these all in affine Lagrangian relations, which Bayes and al. Showed in two of his papers. So, for example, like these inductors, capacitors, and resistors are kind of spiders where A is 0 and then B is like the value of the capacitor, resistor, or inductor. And for this semantics, he works over these real rational functions, which is kind of a technical thing. And then they interpret X as the differential in time, which is like a nice trick. But yeah, so this is kind of my relation to Priya's talk, in my talk. But also you can, if you change the field from the reals or the real rational functions to a finite field of odd prime dimension, then you can interpret these affine Lagrangian relations as stabilizer circuits, where these two spiders you interpret as these sums. And what's interesting about this interpretation is because it lands in complex matrices, you can ask, what's the complex conjugation of if you pull it back along this interpretation back into affine Lagrangian relations, and it's given by this action on these two spiders. So if you have a white spider, it negates both of the phases, and if you have a black spider, it negates the second one. Okay, so now this is on to the new stuff. So in categorical quantum mechanics, Peter Selger had this construction to take kind of a pure quantum thing and introduce discarding. And what he does is he takes some pure quantum thing F, and then he tensors it with the complex conjugation, and then traces by them. And then the way to interpret this is that you have your pure thing F here, it's input and output, and then the part where you trace along is interpreted as like discarding in a quantum sense. So if we were to do this to affine Lagrangian relations over FP here, then doubling it, since we know that it's a semantics for stabilizer circuits, then doubling affine Lagrangian relations would give you a semantics for stabilizer circuits with quantum discarding. And in the literature, this is called stabilizer code. But actually, we can find a bit more of a concise description, which kind of fits within the symplectic picture. So recall that a Lagrangian relation is one that is equal to its own symplectic dual. If we relax this a bit, so we have a bit more degrees of freedom, then we can just ask that it contains its symplectic dual. And in fact, there's a prop of affine coisotropic relations where we relax this requirement. And we can see it as kind of building on affine Lagrangian relations by adding a single extra generator, which is this discarding relation. So it takes the position and momentum and it just relates it to the point. So if we recall the presentation of affine Lagrangian relations, then these are the first two generators, and the third one we add this discarding. So that, but in fact, this quantum doubling, so this taking this doubling in complex matrices or adding the discard relation are the same thing. And we don't have, it doesn't have anything to do with stabilizers or FP. We can do it for any field. So kind of this doubling with respect to the complex conjugation is the same as adding this discard relation. So we can interpret the discard relation, like literally the relation which discards the position and momentum, as the quantum discard. And because of this, now we can talk about, in the quantum setting, measurements. Because if we copy in one of the bases and then discard, then this gives us a projector. So in particular, this projector here projects onto the position basis and just forgets information about the momentum. So following Peter as well, if we split this idempotent, then now we get another type of object, which I'll label in red, and injections and projections out of this object. So this first one, reading from bottom to top, you can kind of interpret this as it takes a position as like a classical value and then kind of inserts it into the quantum state. So that's like your state preparation. And then the transpose of this takes your quantum state, forgets about the momentum, and then just measures the position. So with this, you can give a relational proof of the quantum teleportation algorithm. So like originally in CQM, they have this similar diagram, but it's the setting for this diagram would be in matrices over the complex numbers. But now if we work in this symplectic picture where we split this idempotent, then we can see how quantum teleportation is actually just a relational thing. So on the bottom here, we do a control knot operation on Alice's side, and they share this Bell state here. And then Alice measures the position of the first qubit and the momentum of the second qubit, and sends it over to Bob along these red wires, upon which Bob does a phase correction operation. And then if we just fuse all of these things, then we get that this is the identity. So that's like saying that, so they share a Bell state, and just by communicating two classical bits, they can correct for the errors and then just send the identity channel. So that's like a way of interpreting quantum teleportation. And also this gives semantics for electrical circuits. So if we do this splitting of this projector, but instead of over a finite field, we do it over the real numbers. So affine coisotropic relations over the reals, or over the real rational functions. This gives us a semantics for the controlled voltage and current sources of Guillaume and Pavel. So where you have this current node that takes a real number as the control, and then this voltage thing that takes a real number as a control. And if you relate this to the quantum picture, then this controlled current source is like a phase correction. So it's like these phase corrections here. And then actually the controlled current source, if you flip it around, then that would be in the quantum setting like a non-destructive measurement. So obviously there's something going on, some connection to electrical circuits and stabilizer circuits. And then I'm just going to give a short example, which I don't expect people to digest, just so that I can kind of show you how cool these pictures look. So I said that stabilizer circuits with quantum discarding are called stabilizer codes. And why is that the case? So if you consider this Lagrangian subspace, then we can write it in this form. So in the undoubled picture, it looks like this. So it's actually a coisotropic subspace because we're doing this discarding. And then we can show that using this, we can get this error correction protocol. So where there's on the bottom, here's your logical quantum state. And then you encode it into three more qubits. And then you do like a non-destructive measurement. And then over here is your classical processing, and then you do the phase correction, and then you discard stuff. And then you can do some calculations to show that conditioned on some properties of the errors, then you can correct for them. And then you just get the identity channel again. So it's similar to the quantum teleportation example. Yeah, so in this final example, I kind of pulled the wool over your eyes because, in fact, I never talked about this AND gate. And in our semantics, we didn't actually build what the classical nonlinear control would look like. So we can only do like addition and affine behavior, no multiplication. So one question would be, how do we talk about this kind of coisotropic stuff, but where on the classical wires, the idempotent that we split, where we can do nonlinear stuff, like what is the semantics of that? I have no idea. Second thing to do would be to give an undoubled completeness proof. So similar to in Priya's talk, to give a completeness proof for, just say, affine coisotropic relations over any field. And this would follow the work of Balthazar and Robert and all these people, where they do this for stabilizer circuits in odd prime dimension, which would be equivalent to the case where we fix the field to be FP for P in odd prime. So it's just a matter of just generalizing that a bit. And yeah, another thing to do would be to change the field to something that's not finite and retain a quantum semantics. So maybe combined with this previous point, that would give us a semantics for continuous variable quantum mechanics, or like some kind of fragment of quantum photonics. And another thing I've recently been thinking about is, can we combine the stuff that we've done here with this polyhedral algebra? Because kind of resistors can be seen as like, in this picture can be seen as like slowing things down. And then in the polyhedral picture, they have this interpretation in terms of these networks with capacity. So could you combine these two together to like maybe optimize network problems? And then the final question, which is more reaching, is like, okay, we've doubled once from linear relations to get to Lagrangian relations, and then we've doubled again to get to coisotropic relations. Is there any other kind of doubling we can do, or is that all? So thanks for the talk. That's all.
Thank you, Cole. It's very nice to see these switching diagrams. So is Paulina Gedike here? So if you want to start preparing slides. Okay, so does anyone have questions here in the audience? Questions here? Any online questions before I start asking? No? So I do have a question, Cole. So there is, I wanted to ask you about this red wire that you're using. Is that a primitive of the theory, or is something that you derive?
Yeah, so when you split this idempotent, then it adds a new object. So I'm just using
right.
to
okay, it's the idempotent splitting of that. So the object that you get by splitting that idempotent, right?
Yeah, because it's not apparent.
I see.
In diagrams.
Right. So if you do like an idempotent completion, then you get that object.
Yeah, but you only do it for this.
Right. It's like idempotent completion only for this one.
Yeah, and the identity.
Thank you. Are there any other questions here? Any questions on the online audience? So if you have a question and you're on the online audience, now is the moment to unmute yourself. Okay, if there are not any more questions, let's go to the next speaker. Thank you, Cole.
Yes.